Once again, welcome to the lecture number 5 of the deep learning course. In this particular session, we are going to talk about optimization and particularly about the Lagrange and Kkt condition. So today's lecture, I am going to start with a small question, and let us try to solve this particular simple question and try to understand that what are the important metrics that the people talk about into the machine learning domain. So the question is very simple. Let's assume that you have a box. Let's assume you have a box, and in that box there are 100 images. Okay, so how many images are there? There are 100 images. Few images of them are of, for example, of your interest, and I'm telling that they are of line. There is some line in that particular image. So let's assume that some wildlife photographer has actually collected 100 images, and the line is there into how many? 30 of them. 30 of them contains the line. So 70 means you can know that since 100 are there, so there are 70 where there is no line plus 30 where there is a line. And then what happened that he had actually developed a robot. Let me call it Bob. And the question was asked from the Bob that can you show me all the images of the line. So a model was trained. So you can think that the model, that is, I'm going to call it as Bob, is going to be trained, and he is going to inspect all the images, and after that he is going to give me few images which he thinks that there is a line. So the underlying question, the question here says that he showed me 60. How many images? He showed me 60 images, but line was not there in 40 of them. Means he have actually showed me 40 plus 20 images, means total 60 images he have shown, and the correct images was only 20. Line was not in 40 of them, then the correct images were 20. So this is the scenario. This is a general machine learning scenario when because here you are seeing that your system is having some kind of error. So how come he have shown these 40 images? Because I have asked that show me the line images, but he have shown these 40 images. The system has a problem. So this is a general scenario that happens into the machine learning domain. So whenever this kind of scenario arises, we actually go and make a kind of matrix called the confusion matrix. Very interesting matrix that we actually go and make. In one side there is an experiment, and another side there is a ground truth. So when we are going to talk about this problem, we are thinking that the problem is is a classification problem, and that problem has only two categories or labels. So here, if you go into one side, for example, if you go into this particular direction, one minute. If you go into this particular direction, means what? That you are actually seeing the true, and you are into the experimental setting. You are considering both the true and false. Means what? You are actually neglecting that what has been happened to the truth, to the experiment, and you are actually more interested toward the truth. So what is the truth? Truth is that the line is at how many places? Truth is that if we go into this particular direction, so you are actually changing that what is the ground truth, and ground truth that there are 30 images where there is a line. Similarly, you can see in this particular direction and say that for the false direction, means what is the false? So since 100 images are there, 70 images are such where there is no line. You can again pass into the different direction. You say that from experimental side, I want to say that what is the true. So from the experimental side, you say that your system, the Bob, he has shown you 60 images. So experimental says that who is true? 60 images he has shown me as a true. Similarly, false images. So if he has shown me the 60 images, so remaining 40 images are what? He is telling that there is no line. So based on the experiment, we can come up this kind of matrix. 60, he is telling that in 60 images there is line. However, there is a problem. What is the problem? Few minutes back we have seen that when we have divided and inspected these things, so it was told that line was not there into 40. So we can divide this 60 into 20 plus 40, and we say that this is the wrong thing because 40 was a false. So in this particular table we put that this particular 60, the number 60 can be divided into two parts, I can say that this 40 plus 20. 60 is equal to 40 plus 20, and 40 is false because in these places there is no line, and this 20 is true. Okay. So on the same way, we can also divide this 40 also, this 40 also, and you know that since in my box there were 30 line images and 20 of them has been taken out. So inside the box, what is there? 10 line images plus how much other? Total number of images were 40 inside my box remaining. So 20 plus 30, 10 plus 30. So out of them, 10 is something where there is a line, and for the 30 there is no line. So and this 10 is important because your system was not able to recognize that there is a line. So again, if you go into this particular side, you say that it was true that there was line, but system was actually telling it false. So this is the 10. This 10 comes over here, and this then the 30 comes over here. We say that item which were false, your system is also going to tell you it is false, false, false. This is an important matrix that is called the confusion matrix. Okay. In this confusion matrix, you actually find out multiple things, such as where are the problem areas, where are the areas where my system has done the problem. So you say that your system is going to tell true when your system is going to tell true, but the system, but actually it is false. This is the problematic area. So this is the first problematic area where there is a your system is going to have error, is actually having the error. This is the first problematic area. This is the first problematic area. So these peoples are actually, from your system point of view, these items are actually accepted. Okay, because your system has actually accepted them, and he has told that there is an item, but item was not there. So this acceptance is false acceptance, and you know that false acceptance is called type 2 error. So false acceptance is type 1 error. Okay, we have discussed into the previous classes that if it is a false acceptance, it is a type 1 error. Next kind of problem is here where the item was not there, but we were, I think I am doing mistake. Experimental is telling false. True people's experiment. What is this? True true people's, my experiment is telling false, means this is type 2 error. Yeah, I'm right. So these peoples are actually rejected. These peoples are actually rejected, and this is false rejection, and this is called the type 2 error. In the previous sections, previous classes, we have also discussed that which error is more problematic. Type 1 error is more problematic because these peoples, when they enter to the system, they are not legitimate people, so they can harm to the system. That's why we don't want these people into the system. So more problematic is the T1. However, T2 is also important because if it is not good, then convenience is a problem. Okay, so this is what the setting is. So you understand that what is true positive. True positive means where there are few important metrics. What is true positive? These peoples, 20 peoples, the system was correctly able to tell them. So true positive is 20. True negative, truly negative peoples, the system was telling for them, system was telling that they are negative. Type 1 error, we have few minutes back talked about that. This is the type 1 error is okay. Type 1 error is false positive. Yes, false positive is a type 1 error. Who are the false positive? These are the false positive people. So this is the type 1 error. This is the type 2 error, 10 peoples. Okay, no problem. What is the accuracy of the system? Accuracy is this of the system is this, that the places where my system is correct. What are the places where my system is correct? For these 20 images, my system is correct. But for these 30 images, my system is correct. So the accuracy is 20 plus 30 divided by 100. So by this you can find out the accuracy. What is the precision? Precision is something that whatever answer the system is giving, in that thing how correct the system is. So how much, what is the answer given by the system? These 60 images, and out of them only 20 was the correct answer. So the precision is 20 by 60. Okay, is it clear? Precision means whatever answer the system is giving in that particular set, what is how good the system is. Recall, we wanted all the 30 images, but the system was only able to give 20 of them. How many total images were there? 30 images were there. System was able to only retrieve 20 of them. So the recall says that how much you are actually able to retrieve. So it is 20 divided by 20 plus 10. This 30 images were there. System was able to retrieve 20 of them. Specificity, true negative rate into the same way. True negative means these were the negative area where the things system was able to do that. So, but he was able to correctly only tell about these 30 images that this was actually negative images, and he has since also pointed out this 40 as a negative thing. So total items he was able to tell as a correct negative was 30 plus 40 plus 30. So this is the specificity. Then again, there is a very important measure. Many other time paper reports this, that F score. F score is nothing uh, more than the average of the precision and recall. And there is another measure, that is F1 measure, which is the harmonic mean of the precision and recall. So what happens that when you develop a system, you want to report the how good your system is. So most of the time you use these kind of metrics to tell that how good your system is. Make sense? Any questions on this particular slide? So always remember that if a problem is given to you, you can find out what is the accuracy, precision, recall, specificity, and F score, F1 measure. So you would be so which of these do we use to compare models? Okay, there is a question that which of them we use to compare the model. So as you can see that all of them are actually going to represent a different kind of different perspective of a model. So when you are going to compare a model, you have to see that if the model is very good, then system would be beating on all these parameters. But sometime it may be possible that system would be only beating the other state of the art things only one or two parameters. So that you have to find out all these parameters and report whatever the best that you are going to do. Make sense? All of them you have to compute. Now we want to discuss something about the optimization, and optimization is actually our task. Automatic optimization is actually machine learning. If you can do the optimization into the automatic way, then actually uh, this is the thing we wanted to do into the machine learning. There is a question, let me read it. Sir, if the classes for classification are more than 2, then is the matrix a good approach for running experiment? Then is the matrix is a good approach for running experiment? You want to say that you want to ask that whether the same matrix would be used or not? Okay. So maybe at later point of time we can discuss that what can be done if more than one classes are there. But for all practical purposes, you may think about one versus all approach, where if five things are there, for example, lion, dog, cat, bus, and car. So you build a classifier that talks about that whether it is a car or not, whether it is a lion or not. So then in one category, there would be lion, and in another category, all these things would be there. So instead of using a single classifier that can tell that what particular this item is, you develop multiple classifiers and then use their confidence to tell that uh, what is the actual classification of that particular item is. Make sense? Okay. So if in this way you can transform all the problem into two class classification problem, and then you can apply the same kind of things over there and solve the problem in your hand. Okay. So we are talking about what is optimization, and as you know that into the mathematical domain, it is a technique. that can maximizes or minimizes a function, and that particular function is most of the time we call it a give it a name as an objective function. For example, this is a function z is a variable that tells that this is a function. There is some constant multiplied by x1, constant multiplied by x2. So I can write, for example, 3x1 plus 4x2 minus 3x3. For example, three variables are there where n is equal to 3. I want to find out the maximum value of this particular quantity, provided this there are some constant. I say that value of x1, value of x1 plus x2 plus x3 should be less than 5. Value of 3x1 minus 2x2 plus x3 should be less than 10. So I can write multiple statement also and statement. So if I write like this, I would be creating a tabular structure, and that structure can be that is generally called as a linear programming problem setup. And in this particular setup, we have multiple methods to solve this kind of equations. Here in this setting, most of the time we say that all these x are actually positive, and however, it is not that much required that you put this thing, because in the general scenario the values of these x can also be negative. But as we have seen into the previous sessions also, that any kind of scaling and translation does not make difference into the complexity of the problem. Therefore we safely assume that all these values are actually positive. So this is the setting for the linear programming, and I think that all of you know about this, that what is the optimization and what is this linear programming setup. However, the general functions with which we deal, they are not these kind of linears. Okay. So, and multiple variable when we think that since multiple variables are there, we say that it is a multivariate optimization problem, where we think that this particular function is not linear. Most of the time this function is actually not linear. Linear programming setup is very simple, and there are various linear programming solvers are available. You can use any of them to find out the answer. But in the case when this function is not linear, then we may have some kind of problem. For example, if we have a function that is not a linear function, and we want to find out that what is the maximum or minimum value of this particular function, provided some constant, and let us just assume that a constant of equality constant. For example, there is another function that can define that I want to find out that value of this thing should be equal to this particular constant. So nonlinear function, you can assume there are many such functions. So how can we do that? Okay. So let me tell you that what do I mean by this the optimization process over here. Just assume that let's assume that you have a two-dimensional space. Okay. In the two-dimensional space where x and y, two variables are there. So any item that is any place you can pick. For example, I put this particular point. This point you can draw perpendiculars over there. You can find out what is the value of x and y. And on this value, on this particular place, you can find out that what is the value of the function. So this function would be giving any other value, and you can go upside and put that particular point over here, and by this you create something. Let us assume that we have a circle. We have a ball over here. Let's assume that you have a ball over here. If I ask you that where is the minimum value, okay, can you tell me that where is the minimum value? Definitely the minimum value would be at the bottom of this particular circular region, and that the corresponding point with respect to that particular point is going to give you that what are the optimal parameter of x and y that can actually optimize this particular thing. But sometime what happens, this is actually general scenario, but what in general happens is that this particular restriction actually bounds you that you can only move on some other plane. For example, this is the equation of the plane. Okay, so if it is the equation of a plane, and I ask you that now can you tell me that where is the optimal what is the optimal position, but you cannot move anywhere. Okay, you can only move on this particular plane only. then what would happen? Where would you go? If multiple planes are there, definitely you know that if two planes are there, then if two planes are there, then there would be the intersection, there would be some intersection point of these planes, and then you can only move on that particular line. So definitely you have to in the same way you have to evaluate everywhere and find out that what is the value. So you should understand that this time when I am going to introduce this kind of condition, your minimum would be somewhere here. It would not be at the previous place which was usually it was happened to be. It is going to be at a very different place. What is the property of this particular place? What is the property of this particular place? Can we find out something? Let me tell you. Okay, so let me draw into this two-dimensional space only. Okay, let's assume that in this direction there is a x, and in this direction there is a y. It is a two variable problem where we have to find out what is the optimal value of x and y. Let's assume the optimal value is here. Okay, and what is the optimal value? Let's assume the optimal value is 100. Okay, I'm not sure about this. So my question is, I'm going to ask a very simple question, that what would be the value at this particular place? We are assuming that the function is continuous. Please note that if the function is not continuous, then we cannot do much things in this particular setting. We are assuming the function is continuous. So what would be the value at this particular position? And let's assume that this is the minimum value. Okay, so what would be the value over here? I don't know, but it is fair to assume that the value would be near to 100. We can say that this value is for example 90. It is fair to assume, because it is the highest value. Nearby, it is a continuous function. Nearby values are also going to be the same. Make sense? So if I find out another point nearby, I can get many points where the value is 90. This is not only the one place, many values, because at this particular location the value is 100 and it is optimal. Means what? That nearby it is on all the nearby points it is going to be the maximum. So nearby I can find out a contour on which the value is going to be 90. Make sense? Similarly, if I pick any other point and let's assume that here the value is 60, so I can again construct a contour of the values which are actually 60. Can you tell me that what is the value that we are going to get at this particular point? It would be something between 90 and 60. Let me call it 70. So you can say that there is another contour that talks about the value 70. Here again there is some contour where the value is say 80. Okay, so if I ask you that where is the minimum value, if I ask you where is the minimum value, okay, definitely you know that minimum 1 minute, definitely you know that minimum value is here. But if I say that no, there is a constant, if I say that there is a constant means what? That you cannot go anywhere, you can go on only this particular place. Okay, on this particular line only. If I say that you can only, because of this constant, you can only move on this particular line, then how can you find out the solution? The problem is clear. How can you find out the solution? So you may by yourself can think that okay, it is fine that that there is an there is a point here, the value is 60, here is value is 70, here value is 80. Then since I am going inside this 81, so there may be some other contour that is passing over here and just touching over here, to which I am not going to cross. So this is the point. Actually, this is the point where the value would be optimum. Everybody is okay with that? Can you write yes? If you want to find out the maximum value, provided this constant that you only have to move on this particular red line, so this is the only thing that you have to do, that this is the maximum value. So what could be the maximum value? You know that here by, let's assume that I said that this was 80 and inside is 90, maybe 85 is going to be the maximum value. What is the property of this particular line? What is the property of this line? So let us try to understand. So for everywhere when this particular curve is cutting the contour, what is going to happen? You know that at this particular point the line gradient of this particular line is this and gradient of contour is this. At this particular line, gradient of this particular line is this, and contour, gradient of contour is this. Gradient contour is this, gradient of line is this. But at this point, gradient of line and gradient of contour both are going to be the same. Here also you say that gradient of contour and gradient of line is different. Gradient of contour and gradient of line is different. Gradient of contour and gradient of line are different. So ultimately, what we want, that gradient of this particular function and gradient of this particular g, they are going to be into the same direction. If they are into the same direction, we can say that there is some multiplying factor, and then they are going to be equal. Am I right? So ultimately, the point on which it is going to happen, this kind of condition we are going to have. Make sense? Okay. If we want to find out the optimal value, this kind of condition is going to hold. Make sense? So this is essentially the proposal of Lagrange multiplier. It says that gradient of f minus lambda time gradient of g should be 0, because if it's just a rearrangement of the expression. So ultimately, if we want to, we have understood that if we want to optimize the thing, so that at that particular point, this kind of condition is going to happen. Make sense? So if function are given to us, so we can find out the optimization into this using this kind of problem formulation, and this kind of problem formulation is called the Lagrange multiplier. Okay, Lagrange equation and Lagrange formulation. Let us apply our understanding on this particular problem, and this is a very simple problem. Let the cost of producing X amount of a product A and Y amount of product B is this. There is some expression that says that if you want to produce the X amount of A, let's assume that you are running a company where 2 items are going to be produced, and you want to produce X amount of X amount of A and Y amount of B, then the cost is going to be 6x square plus 12y square. Okay, and we want at least 90 items. This particular thing says that x plus y is equal to 90. Okay, this says that x plus y is equal to 90. So you just make it x plus y minus 90 is equal to 0. So this is the another constant. The two constant we have. First, we want to maximize two equations we have. We want to maximize this particular quantity with the condition that x plus y should be equal to 90. We can do a Lagrange formulation and say that minus of, we can say that minus of lambda time x plus y minus 90 is equal to 0. This is our formulation. So how can we go ahead with this? We can find out the derivative of this particular term, and if you find out derivative with respect to, let me call this function as a L, then I say that derivative with the partial derivative with respect to the x is going to be, what is this value? I think 12x, because x is not otherwhere, minus lambda. What is partial derivative with respect to y? So you can also find out the derivative. I think 24y minus lambda. Am I right? What is partial derivative with respect to lambda? It is again x plus y minus 90. Am I right? So if you want to solve this particular, find out the optimal parameter. So you know that when there is a optimality, at the point when you achieve this optimality, this derivative is going to be 0. You say that 12x minus lambda is equal to 0, means x is equal to lambda by 12. Okay. From this equation, from the second equation in similar way, you can find out that y is equal to lambda upon 24. You put these two values into this particular equation, and I think you can solve and let me know that what is the value. So using this kind of setting, you come up with the answer that x is equal to 60 and y is equal to 30. By this, you would be able to find out that what is the optimal values of these two parameters. Let us see one more example, and this is again you can see that this is nonlinear function. Let's assume that we have 3 variables x, y, and z, and here we have a nonlinear function x square plus x plus 2y square plus 3z square, and we want to find out the maximum value, optimal value maximum or minimum value of this particular thing, provided with the constant, which are actually, you can see that they are also not linear into this particular example. X square plus y square plus z square is equal to 1. These are the general kind of scenarios when we want to find out the optimal values of one equation, and our constant is also not that much straightforward. Okay, how to go ahead with that? Into the same problem setting, we say that I am going to write the Lagrange equation, and this is going to be the first expression, this minus of lambda times this second expression, and then we have to term by term find out the derivative with respect to x, with respect to the x, with respect to y and z and lambda. And these values are 2x plus 1 minus 2 lambda x, 4y minus 2 lambda y, 6z minus 2 lambda z, x square plus y square plus z square minus 1. Okay. Okay. So let us one by one see this expression. So if I consider this particular expression, it says that 4y minus 2 lambda y is equal to 0, because when the things are optimized, it is going to be 0. So I can say that 2y, I can take 2y out, then it becomes 2 minus lambda is equal to 0. So it says that either lambda is equal to, it says that either y is equal to 0, it says that either y is equal to 0 or lambda is equal to 2. Okay, all right. Next expression, we can find out, we can consider this expression, and the similar kind of thing we can obtain from here. 6z minus 2 lambda z is equal to 0. So here if I take 2z out, 2z out, it becomes 3 minus lambda is equal to 0. So again it gives either z is equal to 0 or lambda is equal to 3. So what are the conditions? The condition is this: we want to find out what is the value of these parameters. So I say that the value of y, value of z, what is the value of x, y, z, and what is the value of lambda. We want to find out that. So lambda is not that much important, because point is ultimately if we get the value of x, y, z, it is done. So in this particular setting, what it says that y is equal to 0, and from here I can take z is equal to 0, y is equal to 0, z is equal to 0, or I can take y is equal to 0. I can take y equal to 0, lambda is equal to 3. So I can say that y is equal to 0, lambda is equal to 3. This is the second condition. Third condition, that lambda is equal to 2. Lambda is equal to 2 and z is equal to 0. I say that lambda is equal to 2 and z is equal to 0. What are the value of other parameter? We have to find out. Okay. Next condition, that lambda is equal to 2 and lambda is equal to 3. So it is a absurd thing. So we cannot consider that. So let us forget about that. So we got these kind of scenarios. One by one, we can utilize this scenario and put into the equation. Okay. So if I put this equation, the first expression for the value of y and z is given to me, and I put into this particular equation, what I get. So you see over here that value of y and z is equal to 0. So I say that y is equal to 0 and z is equal to 0. Okay, y and z both are 0. This particular expression need to be equal to 0. So what is the value of x? It is plus minus 1. Am I right? Am I right?
Yes.
So by this we get that x is equal to plus minus 1. What is the value of lambda? That is we are not right now interested, because if we get the value of x, then we are done. Next you see that y is equal to 0 and lambda is equal to 3. Y and lambda, where are y and lambda? So I can come to this particular equation. I can put the value of lambda over here. So what is this? 6z minus 2 lambda z is equal to 0. So 6z minus 2 into, what is lambda? Lambda is 3. Okay, into z is equal to 0. So I think by this I would get 0. So this we have solved. The second case, when y is equal to 0 and lambda is equal to 3. So I can get I can use this expression, and I can put over here 2 multiplied by 2x plus 1 minus 2. What is the lambda? Is 3 into x is equal to 0. So you solve it. I think you would be getting okay. So I will not go into that much detail. I think that is also not required here. So y is equal to 0 and lambda is equal to 3. Using these values, you can find out that what is the value of x and z. So if you apply all these cases, you can get all the values of x, y, and lambda. So ultimately, what you get is this, that from this particular case, you get what? That what is the value of x, what is the value of y, what is the value of z. Here you get the value of x is plus minus 1, so plus 1 minus 1, what is the value of y and z are 0. So 0 0, this is the one point that you come up with. From this expression, what you come up with, x is equal to 1 by 4, so you 1 by 4, and y is equal to 0, so 1 by 4 and 0. And what is the value of z? Is equal to plus minus under root 15 by 4 plus minus under root 15 by 4. Okay. From the third expression, y is plus minus, so you say that x, the value of x is equal to half 1 by 2, and value of x is 1 by 2, y is equal to plus under root 3 by 2 minus under root 3 by 2, 1 by 2, and what is z? Z is equal to 0. So these are the six points that you are going to get as an optimal point. Now your task would be to evaluate, because you know that this particular function and the points are given to you. So you evaluate all these points on this particular function and find out the value. Okay. So let me say this thing, that that point 1 is equal to 100. This point 2 is equal to minus 100. This is the second point. Point 3 is equal to 1 by 4 0 under root 15 by, this is the point 3, this is the point 4, so it's 0.4, 0.5 and 0.6. So this thing we have seen. Okay, that there are 6 points that comes out from this particular understanding. Now I told you that we have to find out that what is the value of this particular this particular expression. So the value is going to be 2. If you find out what is the value on P1, value is going to be, because 100 you put over here, so x is 1, this is 0 0, the answer comes out to be 2. So here it is written as, 2. This part is clear. F2 is equal to 0. What is F2? Minus 1 0 1. So you put it here. So minus 1 is a minus 1 square plus minus 1 plus 0 0. Okay, 0 plus 0, it comes out to be 0. So the value is 0 here. Okay. On the second point, the value is 0. On the third point, you say that 25 by 8. You just find out that what is the value, 25 by 8. You can compute here. Fourth point, 25 by 8. Fifth point, 9 by 4. 6.9 by 4. So these are the values. So what is the maximum value? The maximum value is 25 by 8 and the minimum value is 0. If you want to find out on what point these are maximum or minimum, you just pick that particular point. So 25 by 8 is on P3. So you can say that P3 is 1 by 4 0 under root 15 by 4. This is the point. And similarly, this is the 0, means minimum is at the 0 at the point 2, and point 2 is minus 1 0. So this is an important setting in which you can solve these kind of optimization problem, where your function that you are going to optimize is actually not this particular function is not linear, and but we assume that this function is continuous. So you can apply the method of Lagrange multiplier to solve these kind of problems. We have seen that Lagrange multiplier, the method of Lagrange multiplier can be applied to the conditions when there is a equality constants over here. But sometime in our settings, this equality constants is not there. Okay, into the general setting, it may be possible that when you are going to do the multivariate optimization, then you have to maximize a function where GIs means the functions which are actually constants, they are actually not equality, they are inequalities. So without loss of generality, again we can think that these inequalities are going to talk about that all these values are actually less than this you can always make, because if the inequality is there, you can always find out the suitable parameter to multiply and make this into this particular format. So here our assumption is, again our assumption is this, that this x is not a single variable, it is a transpose of, it is a multivariate that have multiple attributes, and it is coming from the Rn, and we also assume that these functions are continuous. Okay, however we know that they are not linear, they are non-linear, but they are continuous. So one problem setting we can use is this, that we can introduce some slack variables. What do I mean by slack variable? That you introduce some extra parameter at this particular place. You say that there are few more parameters, and when you come up with these values, you neglect them value with those values. So you formulate the problem and introduce more variables to the system, and when you solve this thing, you are not actually taking you are not interested into the value of whatever the value has been obtained. What is the importance of this those things is this, that when it is going to be told as a less than equal to 0, you can add a positive constant. How can you make sure that it is a positive constant? You say that there is a variable and you are going to add a square of that particular variable to the gj, and by this particular part becomes equal to 0. So okay, so you are going to convert this expression, you are going to convert this expression to this particular expression, where you are going to say that equality constants are actually met. When you change this problem into this particular setting, this reduces to the problem of the classical optimization problem that few minutes back we have seen. And in this particular setting, we have also talked about that we can formulate using the same mathematical notation of the uh, Lagrange formulation. So you can write this in once again, that use this particular function fx plus summation of these constants, and these constants are this, again this is the constant. You put, instead of the single variable, you are going to put the expression into this particular format. So this is a general problem setting. In this particular in this general problem setting, again you have to find out that what are the derivative with respect to the each of the parameters. So this is the equation that we have seen into the previous slide, the function, and then there are m small m number of different constants. So this is the equation that we have just seen. Again you have to apply the partial derivatives with the Lagrange partial derivative with respect to each of these attributes. So if you find out this, so it is del f upon del xi, and then you again apply over here. So there you get that there is a partial derivative term that comes, because since it is a constant, it goes away. Only partial derivative of this particular term remains. This being constant comes out, and this kind of expression you get, which need to be 0. When you do a partial derivative with respect to the lambda, so this term goes away. So this and this also goes away, because there is no lambda over here. There is also no lambda uh, inside, but because of this multiplication, only this term remains. Okay, inside terms remains. So you say that gjsj square is equal to 0. Okay, if you pick a particular lambda, so many terms would be there. Only that particular lambda would survive. Okay, lambda 1, then only lambda 1 related term would survive, and all other things would actually go away. So this is another condition that comes for our optimality. The third thing is this, that if you when you do a partial derivative with respect to the sj's. So you get this term, that you see that because there is no sj, there is no sj over here, they become 0. So lambda time sj square. So and this is sj square. So if you do the derivative, 2 times sj, 2 times sj lambda j is equal to 0. And since 2 is there, it actually goes away. So you say that lambda j sj is equal to 0. These three conditions, you have to find out the solution based on these three conditions. And these three conditions are called the uh, Karush-Kuntukar condition, KKT, Karush-Kuntukar condition, or KKT condition in general. So if these three conditions, based on these three conditions, if you can find out the solution, so you are going to get the uh, optimal solution. This is actually, this is only the necessary condition, that on the any of the point, if there is a optimal solution, then these things are going to happen. And sometimes we also call these conditions as with the name, such as this condition, that lambda j sj is equal to 0 as a complementary slackness condition, and this condition is called the feasibility condition, and this is the optimality, means optimality condition. So based on these three conditions, if we find out the solution, so if there is a solution at that particular point, all these conditions are going to satisfy. Okay. So it is a necessary condition, but we actually want to find out the solution. So who guarantees that we are going to get the solution? Okay, who guarantees that if we are going to solve something using this kind of condition, whether we are going to get the right solution or not? The answer is that if we say that my function is convex, okay, if this particular function, that the functions which are given to me, they are convex, then we can find out the solution. Okay, if fx is convex, then feasible space, and the feasible space is convex, then we can find out, we can tell that any solution that has been obtained based on these conditions is going to be the optimal solution. Just for the sake of completeness, what is the convex function? If I want to give you the idea that what the convex function, so this is a diagram where on one side there is x, a variable, and another side there is a function of x. So if I draw the function of x, let's assume that the function of x is this. Okay, so the convexity says that you pick any 2 points, x1 and x2, and you measure that what is the value over here. So here the value is, what is the value? It is fx1. Here the value is fx2. So if I pick any point in between, I can represent that point, maybe I say that x dash, I can represent is x1 multiplied by lambda plus 1 minus lambda time x2. Okay, but if I put any value lambda from 0 to 1, so if I put the 0, then what would happen? That it would become x2. If I put 1, it becomes x1. So using the value of lambda, this point can get anything between in any place into between of this thing, this range. So if this is the point on which I am going to consider, so I can again measure that what is this value. What is this value? This value is function of x dash, or function of, I can say that it is lambda, it is lambda time x1 plus 1 minus lambda time x2. This is what this is. Okay, in the same way, I can draw a line over here and find out that what is the related point at this particular place. Again, I can write that lambda type this, and 1 minus lambda time fx2. Okay, so this second part is actually greater than the value of the function. Means what? That if I want to see that what is the value of at this particular point, is it less than the linear combination of these point at the place at which this point is there. So if this condition satisfies, then I say that this kind of function, this function f is a convex function. So if the function is convex, the point is this: if the function is convex, and we are going to find out the solution based on these equations, our solution is going to be optimal. This is called the Kkt condition, and very important optimization problem, optimization theory. Okay. That's all for today. Thank you very much for the joining.